So today's lesson is about cyclic quadrilaterals. Okay. Uh, so any quadrilateral that the vertices lies in a same circle is known as a cyclic quadrilateral. So if you look at the first diagram here, that A, B, C, D points. Okay, I'll speak loud. Uh, okay, if you look at the first diagram, uh, that the A, B, C, D points are lie on the same circle. So that quadrilateral is known as a cyclic quadrilateral. That's the only condition. Okay. So what cyclic condition to be a cyclic quadrilateral is that all the vertices must lie on a same circle. That's it. So if you look at the second diagram, P, Q, R, S, all the vertices are lie in the same circle. So that is also a cyclic quadrilateral. And if you look at the third diagram, K, L, M vertices are lie on the same circle, but N is not. So third diagram will not be a cyclic quadrilateral. And if you look at the fourth diagram, S, T, U vertices are lie on the same circle, but not V. So it is not a cyclic quadrilateral either. So only first and second quadrilaterals are known as the cyclic quadrilaterals. Uh, right. So we'll move on to the next slide. Okay, we have a theorem about this. We have the first theorem about cyclic quadrilaterals. That the theorem says the opposite angles of a cyclic quadrilateral are supplementary. The opposite angles of a cyclic quadrilaterals are supplementary. Uh, that means, uh, okay, the theorem says the opposite angles of a cyclic quadrilateral should be supplementary. We'll see what that means. If we take a cyclic quadrilateral, here we have a cyclic quadrilateral A, B, C, D, and we have the internal angles as P, Q, R, and S. So the theorem says this S angle should S angle plus Q angle should be equal to 120, so 180, and R angle plus P angle should be equal to 180. Here they have the vertices notation. That means ABC, this P angle, plus CDA, the R angle, the sum of that should be equal to 180. And again, DCB, the Q angle, and the DAB, the S angle, the sum of those two should be equal to 180. So that is the first theorem. Okay, that is a theorem. That is also a property of cyclic quadrilaterals. Here we have the first example. You guys can try, but what they're asking for is they have given this BOD as 230, and they are asking for the values of x and y. They are asking for the values of x and y. You guys can do that. I have done this example here. So first we can say BOD, this minor angle, should be equal to 360 minus 230, which is equal to 130. Okay, so BOD, acute angle, not acute. This angle is reflexive angle. This is 130. And from the theorems about the circles, the last session we have learned that this angle subtended on the center point is twice than the angle subtended on the circle by the same arc. So BOD should be equal to 2 times x. BOD should equals to 2 times x. That means x is equal to 130 minus 30 divided by 2, which is 65. Okay, so you can find the x easily, and to find y we can use the theorem that we just learned. So x plus y, the opposite angles, should be supplementary. That means the sum of those two should be equal to 180. So y should be equal to 180 minus x, which is 65. So that gives y as 115. So that's how you do an example. Okay, so we'll move on. We have another example here. Here we are asked to find x, y, and z angles. We have x, y, and z, both all the angles to find. So how do we proceed? I have done this, so I'll show you the steps. Here you can see RTU. The RTU angle is 90 degrees. Why? The RU is a diameter for this circle. So uh, the angle of a semicircle is 90 degrees. So RTU is 90. And from the interior, sum of the interior angles of this RTU triangle, you can see 90 plus 34 plus z is equal to 180. Interior sum of the interior angles of a triangle. So that gives z as that gives c is equal to 56 degrees. Okay, so we have found c. Yeah, so then we can again see RBU angle is also equal to 90 degrees. Why? Again, RU is a diameter. So angle of a semicircle, angle of the semicircle, RBU is equal to 90 degrees. Then considering the sum of interior angles of this RVU triangle, we can see 90 plus 27 plus x is equal to 180. We can solve the equation and get x as 63. X is equal to 60 degrees. So we have calculate the x and z. We have y left. So you can see this R TURS quadrilateral is a cyclic quadrilateral. Why? All the four vertices are lie on this same circle. So RSTU quadrilateral is a cyclic quadrilateral. That means the opposite angles are supplementary. That means angle Z plus angle RST is equal to 180. And we can proceed this since this RST triangle is an isosceles triangle, this RTS angle is also equal to y. And then considering the sum of interior angles of this RST triangle, you can write y plus angle RST is equal to 180. That means RST plus 2y is equal to 180. So we have this 1 and 2 equations. Right side we have 120, 180 on both. So we can say that two left sides also should be equal. So that we can write RST plus Z is equal to RST plus 2y. So we can cut RST from the both sides. That gives Z is equal to 2 times y. So y is 56. Sorry, Z is 56. So y is equal to half of 56. So y is equal to 28. So any questions from this example? You guys can always ask if you have any questions. I hope not. I hope you all got this example without a doubt. If you have any doubt, you can always use the raise hand option and ask anything. Okay, so we'll move on. Okay, here we come to another theorem regarding this cyclic quadrilaterals. So this theorem says if the opposite angles of a quadrilateral are supplementary, then the vertices on the quadrilateral are on the circle. That means the inverse or the converse of the previous theorem. That means in the first theorem we said that if any quadrilateral is a cyclic quadrilateral, their opposite angles should be supplementary. Here we are saying the vice versa. If the opposite angles of any quadrilateral are supplementary, then the vertices of that quadrilateral are lie on a same circle, lie on any circle. Okay, so we can again uh, do a example using that, because no need to describe that. That is the vice versa of the previously discussed theorem. So here we are asked to find, we are asked to prove that CDFE is a cyclic quadrilateral. We can see that ABCD is a cyclic quadrilateral because those vertices are lie on a circle, but we cannot see any circle uh, around CDFE. So we are asked to prove that CDFE is a cyclic quadrilateral. So CDFE is this quadrilateral. So what we can do, I'll show you the steps. We can write CEF angle and AEF are sum of that equals to 180. Why? Because CEF and AEF are on the angles of a straight line. That those sum of those two angles are equal to 180. Okay, so next we can write AEF is equal to CAB. AEF is equal to CAB. Why? Because because of these two parallel lines, they are alternate angles. Then we can say CDF is equal to CAB. These two angles, because CDB and CAB are angles of a same we can say same angle subtended by same arc. So CDF and CAB are equal. Then we can write AEF is equal to CDF. Why? Because this CAB is equal to AEF. Again, CAB is equal to CDF. So that AEF is equal to CDF from the axioms. Then we can write CEF. We have at what time the class will end. Okay, so we were discussing, we can write CEF plus CDF is equal to 180. Why? We wrote CEF plus AEF is equal to 180. Now we have proved that AEF is equal to CDF. So we can substitute CDF instead of AEF. So CEF plus CDF is equal to 180. So what are those two angles? CEF plus CDF is equal to 180. So the opposite angles of this quadrilateral are now supplementary. That means this CDFE quadrilateral is a cyclic quadrilateral. Okay, I have not stated that sentence here. You have to write that. Okay, so if you have any doubt or anything to ask regarding this example, you can use the raise hand and ask. Okay, I hope not. I hope you all got the example. So let's move on. Okay, we have another theorem regarding this cyclic quadrilaterals. So this theorem says if one side of a cyclic quadrilateral is produced, the exterior angle so formed is equal to the interior opposite angle of the quadrilateral. If one side of a cyclic quadrilateral is produced, the exterior angle so formed is equal to the interior opposite angle of the quadrilateral. So we'll look into a graph diagram and see what is that. So here we have a cyclic quadrilateral A, B, C, D, and here all these sides are produced. AD is produced to N, DC is produced to M, CB is produced to L, BA is produced to K. The theorem said that if any side is produced, the exterior angle so formed is equal to the interior opposite angle of the quadrilateral. That means if you consider this angle, the interior opposite angle would be this. So the theorem says these two angles are equal. Okay, so using that, you can say this DAK is equal to BCD, DAK is equal to BCD, and ABL is equal to CDA, ABL, this angle is equal to CDA, this angle, and BCM is equal to BAD. So BCM, this angle is equal to BAD, this angle, interior opposite angle. And also this CDN is equal to the interior opposite angle ABC. Okay. Uh, can you explain it again? Okay. So I we have discussed a theorem. The theorem said that if one side of a cyclic quadrilateral is produced, the exterior angle so formed is equal to the interior opposite angle of the quadrilateral. This is the theorem. So uh, we are considering a diagram to understand that. So we have a cyclic quadrilateral ABCD, and if all the sides are produced, so if we consider any so formed exterior angle like this, the theorem says this angle is equal to interior opposite angle of that quadrilateral. That means this. Okay, so this angle and this angle are equal. That's what the theorem said. Okay, so all the angles can all the so formed in exterior angles can be explained like that. So DAK is equal to BCD, ABL is equal to CDA, BCM is equal to BAD, and CDN is equal to ABC. Right. So I hope you got that now. Uh, so we can use this theorem to solve some examples. So we have here we have an example. We are asked to find P, Q, and R. Okay. So here you can see one and two cyclic quadrilaterals. This one and this one is a cyclic quadrilateral, and this one is also a cyclic quadrilateral. Okay, we just identified there are two cyclic quadrilaterals. So how do we do this? I'll show you the steps. So uh, Q is 70. So how do I write Q is 70? So we have a cyclic quadrilateral here. This is a produced side. This is the so formed exterior angle that should be equal to interior opposite angle, which is Q. So we can directly write Q is equal to 70 degrees using the theorem. Okay, I hope you got that. Mm, so Q is equal to 70 degrees. So now we have to find only, so we have to find P and R. Okay, so if you consider this, the next cyclic quadrilateral, this R and 130, uh, I didn't understand that. So okay, I'll repeat the above step how we got this Q is equal to 70. See, you have a cyclic quadrilateral here. This I'm drawing on that. So this is a cyclic quadrilateral because the four vertices are lie on the same circle. So this is a cyclic quadrilateral without a doubt. And the theorem we just discussed says that if any side is produced in this cyclic quadrilateral, this side is produced. We have produced this side. So any side is produced, the exterior angle so formed here, this is the exterior angle. Exterior angle so formed is equal to the internal opposite angle. Here we have internal opposite angle. We have the internal opposite angle as Q. So the theorem said the so formed exterior angle is equal to the interior opposite angle. So we can directly write Q is equal to 70 degrees. Okay. I hope you got that now. Okay. We'll move into the next part. I'll erase this. Okay. So the next step to find ROP, if you consider the other cyclic quadrilateral left in this diagram, which is the one I drawing on right now, here in this cyclic quadrilateral we have two opposite angles as R and 130. R and 130 are opposite angles of this cyclic quadrilateral. So we can say in the first theorem the first theorem said that the opposite angle, sum of the opposite angles of a cyclic quadrilateral is supplementary. So R plus 100 R plus 130 should be equal to 180. So simplifying that, we can get R as 50. Okay. So this one is regarding the very first theorem we discussed today. Okay, so we have only P to find. I'll erase this. We have P to find. So considering this triangle, PQR are the interior angles of this triangle. So we know that sum of the interior angles of a triangle is equal to 180. So we are using that relationship here. So P plus Q plus R is equal to 180. So substituting for Q and R, you can find P as 60 degrees. I hope you get that thing. If you have any doubt regarding this example, you can ask now. Okay, I hope not. So we can move on. Okay, we have a quite large problem here. I'll give you some time to work on this problem and then we'll discuss. I'll give you about 3 to 5 minutes. You can do this and then we can discuss. Okay. So, meanwhile, if you have any question, you can always ask. Okay. Yes. Okay. If we consider this problem, the problem says the center of the given circle is O, the diameter AB and the chord PR intersects perpendicularly at L. The line segment QR and AB intersects at T. If QTA is X, write in terms of the magnitude of LRT and the magnitude of OPQ. Okay, so this angle is X as they have given. So we have to find LRT and OPQ. So LTR we can write X because the uh, opposite angles, right? So this angle is equal to X and LR is equal to 90 degrees because AB and PR are intersecting perpendicularly. So if you consider this TLR triangle, you can write 90 plus X plus LRT is equal to 180. So simplifying that, you can get LRT is equal to 90 minus X. Okay. Uh, I hope you all can understand that. If you have any questions, please feel free to ask. Okay, so now we have found LRT in terms of X. LRT is equal to 90 minus X. So we'll move on to OPQ. OPQ. So to find OPQ, you have to draw this OP radius, and I'll construct a PB code as well, and the BR, so that I can see a cyclic quadrilateral PBRQ here. Okay, so you can always do any construction uh, to see anything that you cannot see without that. Okay, so OP is equal to OB because both are AD of the circle, and OPB is equal to OBP because since OP is equal to OB, the OPB triangle is an isosceles triangle, so that OPB is equal to OBP. Then OPB is equal to 90 minus BPL, right? OPB, this angle is equal to 90 minus BPL because this so OPP is equal to 90 minus BPL. From the geometry you can see, and PL is equal to LR because this OL is perpendicular to the chord PR, and that is drawn from the center point. So that bisects the PR segment. So PL is equal to LR. And using that, you can say this BLP and BLR triangles are uh, conjunct. I don't get the word. So these two triangles are equal. Then using that, you can say BPL is equal to BRL. These two small angles also are equal. Then you can write using OPQ plus OPB plus LRT plus LRB is equal to 180, because this BPQR is a cyclic quadrilateral and two opposite angles are should be supplementary. So we have written that. And instead of LRT, we can put 90 minus X. And instead of OBB, we can write 90 minus BPL. Then we can get, we have substituted and simplified. So you can see OPQ is equal to X. If you simplify this equation, BPL to BPL is gone. Minus 90 minus 90 is minus 180, plus 180, it makes 0. So OPQ is equal to X. So there can be any different ways to solve this problem. This is what I came up with. So if you have any doubt regarding this, you can ask, or if you have any other methods, you can share with us. I'll leave this for a minute if anyone of you are writing this down. Here the question says QTA angle is equal to X. That's fine, right? QTA is equal to X. I have marked it here. So you can directly say this LTR is equal to X, right? The opposite angles, right? In the when the two lines are intersecting, the opposite angles are equal. So LTR is equal to X, and TLR is 90 degrees. Again, the opposite angles. Since PLB is 90 degrees, TLR also should be 90 degrees. Then, if you consider the sum of interior angles of this triangle, you can write 90 plus X plus LRT, this one, is equal to 180, sum of the interior angles of a triangle. So by simplifying that, you can get LRT is equal to 90 minus X. 180 minus 90 is 90. So 90 minus X is equal to LRT. So I hope you got the answer for your question. LRT is equal to LRT is equal to 90 minus X. Okay. So we'll move on to the Roman number 2. Find the magnitude of OPQ. OPQ. To find that, we have to construct this OP radius, because then only you can see this OPQ angle, right? This is OPQ angle. And I will construct these two line segments as well, so that I can see a cyclic quadrilateral in my diagram. The PBRQ will be a cyclic quadrilateral because all the vertices are lie on the same this circle. So then PBRQ will be a cyclic quadrilateral. Now I can write OP is equal to OB, because OP and OB both are radii of this circle. OP is equal to OB. And we can write, so since OP is equal to OB, this OPB angle will be an isosceles triangle. So these two angles should be equal. So OPB and OBP angles must be equal. So I have stated that here. Then we can write, before that I'll mention another thing. You can see this OPB angle, sorry, OBP angle, this one, considering this triangle, this OBP angle is equal to 90 minus B, sorry, I'll write, yeah, BPL, right? This angle is equal to 90 minus this one. Okay, you can write the sum of interior angles of this BPL triangle and get that expression. So OBP is equal to 90 minus BPL. Then I will substitute that expression instead of this OBP here. Then I can get OPB is equal to 90 minus BPL. Okay, I hope you guys don't have any doubt regarding that. If you have, please ask. Uh, so this one is okay now. We can proceed. So PL is equal to LR. That means this is a chord and this is a normal drawn from the center point to this chord. So theorems regarding the circle says that any normal drawn from the center point to a chord bisects the chord, so that PL is equal to LR. So that line is okay. So using that, if you consider this BPL and BRL triangles, these two are equal, these angles are equal, and this is a common line, it's common side. So these two triangles, you can write this. Okay, then using that you can write this BPL angle is equal to BRL angle. BPL angle, this one, is equal to BRL, this one. Okay, these two triangles are equal. I'll state this angle and this angle are equal. Okay, then we can write, since we have a cyclic quadrilateral here, the sum of two opposite angles are supplementary. So this angle and this angle must be supplementary, right? So this angle consists of 1, 2, 3 angles. This angle consists of 2 angles, or you can write this one as one angle as well. Right, so I have stated that one here. So OPQ is this one, OPQ plus OPB. OPB is this one, that makes this full interior angle, plus LRT, it is this, and BLR, that is this one. Those two makes this full interior angle. So this sum of two interior angles must be supplementary. it should equal to 180 because this the BPQR is a cyclic quadrilateral. So that part is also okay. Then we can subject OPQ by uh, sending all the other terms into the right side. So 180 minus OPB minus. Instead of this LRT, I will put 90 minus X because it is proven, and BRL. Okay, so further simplification, instead of this OPB, I can write 90 minus BPL because it's all also proven here. Uh, instead of OPB, I can write 90 minus BPL. That one is also okay now. So if you distribute the, or if you simplify the parenthesis, you can get something like this, and you can see this 9 BPL to BPL plus BPL to minus BPL, minus 90 minus 90 is minus 180, and this is plus 180. So this part is also cancels out. So you will end up as OPQ is equal to X. Right, I hope you got that. If you have any questions, please state here. I'll leave this slide for a bit. In that, please ask. Okay, I hope not. So we can go to the next part of this lesson. We'll move on.